Quantum computers seem to be all the hype, but they have one major drawback. They're extremely fragile, to the point where any disruption could ruin the entire system and cause the quantum particles to decohere or lose their quantumness. Current quantum computers need thousands of error corrections just to perform a simple calculation. That's what makes topological quantum computers so exciting. Their inherent hardware is more stable than standard quantum particles. Hold up though, we still haven't gone over what topology is. Topology is a field of mathematics that studies the fundamental properties of spaces and objects that remain unchanged during continuous deformations, like stretching or bending. For example, to a topologist, a coffee cup and a bagel are fundamentally the same thing, since they both have one hole, and you can go from a bagel to a coffee cup by stretching without actually having to tear the object. This mathematical property of shape is incredibly stable, even at the subatomic level. Topological quantum computers leverage the unchanging nature of topology to help create more stable quantum computers. They use exotic particles called anyons. When you move them around each other, literally braiding them through space-time, you're performing quantum calculations. Each crossover represents a fundamental logic gate in a quantum calculation, such as NOT or AND. The final pattern of the braid is the result of the program. Here's an example. Imagine these strings are paths of two anyons, right now parallel. This is our starting state. To compute, we braid them. This crossover is a quantum logic gate. And now the magic, topological protection. Environmental noise can't destroy the computation because it can't change the fundamental braiding topology. This allows topological quantum computers to be more naturally fault tolerant. We're not just building better quantum computers, we're learning to compute with the mathematics of space itself.